Hello and welcome to today's video. In this video, we're going to have a look at a couple of examples about computing a basis and the dimension of a given vector space. We are going to start with the classic example of a system of linear equations and its solution space. We already know that the solution space is a linear subspace of R to the n for a homogeneous system, with n being the number of variables. Another question is often, can the solution space be represented in a compact way? Usually as the span of a basis of that solution space. We are now going to discuss the question of how to compute the basis for such a solution space before we then turn to a different example that we'll solve using similar means. So this section is about examples for basis and dimension. And we'll start with the system of linear equations in the first part. Consider the following system of linear equations. And I'll give you a system that is already in echelon form because you know how to solve this already. So we won't bother with that. So here is the tableau form of our system. And remember, we are at this point only talking about homogeneous systems, so the right-hand side is 0. Now, the solution space of that system is a subspace of R to the 5th, because we have 5 columns, so 5 variables in that system. We'll call the solution space S, so S is a subset of R to the 5th. The system is already in echelon form, and it has 2 pivot elements. Let me just copy the tableau. And then I can show you the pivot elements here. Here's the first pivot in the first row that has a pivot element. And here's one in the second row. The other 2 rows are 0 rows, so there's no pivot element in there. Right? And this is our echelon form. So you can see the staircases here. We have 2 pivot elements. That means we know the dimension of our solution space already. You remember the dimension of the solution space is the number of variables, the number of columns, minus the rank. And the rank is the number of pivot elements. So in this case, we have 5 variables minus 2. 2 is the number of pivot elements. So the solution space has a dimension of 3. The dimension of S is 5 minus 2. That's 3. And the 5 is the number of variables. That 2 here is the rank or the number of pivots. So we do know the dimension. Of course, the question is now we'd like to obtain a basis for that solution space. And how do we go about that? basically what we have to do is we have to solve the system and then represent the solution in a suitable way. If we look at that system again, what we can see here is we have these two pivots here. Those correspond to x1 and x2. And we have these three columns here that do not have a pivot. Let's copy that once again. And make a quick note. So these are the pivot elements, right? And here we have no pivots in those columns. That means the corresponding variables are free variables. So we just denote the variables by x1, x2, x3, x4, x5. And that means x3, x4, x5 are free variables. And then we can solve for x2 and x1 through backwards substitution. So x2, we solve that second row here, we solve that for x2. And if we do that, we get x2 equals minus x3 plus 4x4 plus x5. And then we solve the first row for x1. And here we get x1 equals 2x3 minus 3x4. And there's a 0 coefficient in front of x5, so that doesn't appear in the solution. We are now ready to write down the solution space. So S has the form where x1 is 2x3 minus 3x4. x2 is minus x3 plus 4x4 plus x5. And x3, x4, and x5 are free variables. So they can assume any value you want, any value in the real numbers, of course. Now the solution space can be written in a way that is a little bit nicer and a little bit more suitable for seeing what the right basis is. What we can do is we can split that vector into components that have an x3 part, an x4 part, and an x5 part. And we do just that now. So we collect all x3s in one vector. And here we have a 2 here, a -1 here, and a 1 here. And no x3 in the remaining 2 rows. So this is 2, -1, 1, and 2 zeros. Then we collect the x4 parts. So here we have -3, +4, no x4 here, 1, and 0. So -3, 4, 0, 1, 0. And finally, the x5 parts. There's no x5 in the first row. 1 here, no x5s here, and 1 here. So we get, we get x5 times 0, 1, 0, 0, and 1. Now what do we have here? Well, basically, this part here is a linear combination of this vector, and this vector here. And as our x is the coefficient in front of those vectors, can assume any real number as a value. What we have here is effectively the set of all possible linear combinations of those three vectors. So in other words, this is the same thing as the span of 2 minus 1, 1, 0, 0, minus 3, 4, 0, 1, 0, and 0, 1, 0, 0, 1. So obviously this set here is a generator of the solution space because its span is equal to the solution space. Now the question is that a basis as well? And for a basis, remember we need that set generates the desired space. That is the case here. And also that it's linearly independent. So let's check that second part. Are those three vectors linearly independent? Well, to do that, to check that, what we need to do is we need to see if we can combine the zero vector in a different way from taking 0 times each of those three vectors. So we set up an arbitrary linear combination that combines the zero vector and then see if there is a solution other than setting all the coefficients to 0. To do that, let's see, we need those three vectors, 2, minus 1, 1, 0, 0, minus 3, 4, 0, 1, 0, and 0, 1, 0, 0, 1. We want that to be the zero vector, and of course we need coefficients as well. So we put a lambda 1 in front of the first vector, a lambda 2 in front of the second one, and a lambda 3 in front of the third one. Now let's see if we can find a solution for those lambdas that is not all zeros. If we look closely at that system of linear equations, what we can see is in the last row, this one here, this last row immediately yields the equation lambda 3 equals 0. So there's no other possibility for lambda 3. If we look at the second to last row, this one here, then we see the equation lambda 2 equals 0. Again, no other possibility. Now, of course, that also works here for the third row, the middle row. That yields lambda 1 equals 0. So there's only one possible solution. All lambdas are 0. And that means the vectors, the set of vectors here, is linearly independent. Okay, so those vectors here, 2, minus 1, 1, 0, 0, minus 3, 4, 0, 1, 0, and 0, 1, 0, 0, 1 is linearly independent. And that's exactly what we wanted, because that means we have found a basis for our solution set. And that is just this set of three vectors. 2, minus 1, 1, 0, 0. Minus 3, 4, 0, 1, 0. And 0, 1, 0, 0, 1. So that's the desired basis for our solution space. If we look back at this proof of linear independence, then you can of course see that this will always work in a setting like this. Because what we did basically is we took those rows where the free variable is the only entry. And there's always, for each free variable, there's always one such row. Here's the row for x5. Here's the row for x4 and the row for x3. Yeah, it corresponds to this position here, this one entry. That one entry comes from these entries here. And each free variable always produces an entry like that in the solution. So you always have the property that these vectors that belong to the free variables, in a way, those are always going to be linearly independent because that structure will always be there. So once you have that solution here, once you have those vectors, you know this has to be a basis because the proof of linear independence will always be the same. And of course, once you realize that, you don't have to do that proof anymore. Yeah, so I won't do that anymore in the future. For our second example, we are going to consider a different situation. We're going to consider a vector space that is already given through a generator, but that generator might not be a basis. So the question is, how do we obtain a basis from a generator that may be too large? Or, of course, how would we find out whether the generator is actually too large? So let's consider the following example. Let M be a vector space, and let M be given as the span of the following vectors: 2, 1, 3, 4, 1, minus 1, 2, 3, 3, minus 2, 3, 0. This is a vector space that is the subset of R3. And our task is to determine the dimension of M and a basis. Now, as you can see, we have a generator that encompasses 4 vectors. The dimension of R3 is 3. So a basis in R3 will have only 3 elements. So that means this is surely not a basis, it's too large. M might be the same as R3, or M might also be smaller. So it could be 2-dimensional, it could be 1-dimensional, probably not 0-dimensional. And it could be 3-dimensional, of course. We don't really know what is the case at this point. But we do know that from these 4 vectors, we can eliminate at least one, maybe more. So we can try to obtain different vectors that have the same span and that are linearly independent. So this is the main idea here. Obtain linearly independent vectors with the same span. And we are going to do this through successive linear combinations. More precisely, what I mean by that is I'd like to replace a vector by a linear combination of that vector and some other vector in one step. I'd like to do this in a way that retains all the information, so that means the vector I'm replacing needs to appear in that linear combination with a factor other than 0. Otherwise, that information would be lost forever. And I'd like to do it in a systematic way, such that I will be able to identify vectors that are really not necessary to create that same span. So the idea is to combine vectors in a way that eliminates vectors, meaning they become 0 vectors in the process. So once again, what I'm going to do is I'm going to replace a vector by a linear combination of that vector that includes that vector and some other vector. So the coefficient of that specific vector that is going to be replaced must not be 0. And some other vector in the generator. And I'm going to do this in a way that simplifies those vectors. So I want simpler vectors with the same span. And by simpler, what I mean specifically is vectors with more zeros in their entries. And more specifically, if I obtain a vector that only has zeros, then I can, of course, eliminate that vector. I can get rid of that one. So let's try this with the vectors that we have here. Remember, the vectors were 2, 1, 3, 4, 1, -1, 2, 3, 3, and -2, 3, 0. We'll refer to those as V1, V2, V3, and V4. And now let's start the replacement process. I'll first look at this first coordinate of all the vectors. And I can see here, they all have a 2, a -2, or a 4. So I can use one of the vectors to produce zeros in that first row for all the others. And that's what I'm going to do. I'm going to use the first vector specifically. And I'm going to replace vector v2 by v2 minus 2v1. I'm going to replace v3 by v3 minus v1. And v4 by v4 plus v1. And notice that new combination always includes the original vector with a coefficient that is not 0. And that way we'll obtain a new system of vectors that has the same span as our original system. But we'll look at it simpler because there's going to be more zeros in there. So what we get here is the first vector that remains untouched. The second vector, 4, 1, -1, -2 times the first vector, so we have 4 minus 4, that is 0. 1 minus 2, that's minus 1, and minus 1 minus 6, that is minus 7. So one more 0 here. For the second vector, we obtain 0, 2, 0. So we even get 2 more zeros by chance, but not bad. And for the third vector, we get 0, 4, and 3. So in this case, we don't obtain more zeros. We just kind of simplify that because the zeros are now all in the same row. Still, that looks a little nicer, but it's still not obvious what a base is in the vectors may be. So next step, we look at the second coordinate, this one here. And now there's one particularly simple vector, that is this one, that just has a non-zero entry here. So what we can do is we can multiply that vector by 1 over 2 to get a 1, and then use that to get zeros and everywhere else. So that's what we're doing. In this first step, we just do the simple multiplication. And now we're going to manipulate the other vectors again. We're going to add the vector here. And we're going to subtract the vector here with a factor of 4. And that yields 2, 1, 3, 0, 0, minus 7, 0, 1, 0, and 0, 0, 3. Notice I did not change the first vector. That's just a deliberate choice. I could have done that as well. So last but not least, this vector here and this vector have non-zeros only in the last coordinate. So we can use one of those to eliminate the other completely. And that's what we're doing. Let's say we take this vector here, add it to that second vector, and we need to do this with a factor of 7 over 3 to actually eliminate that vector. And that yields 2, 1, 3, 0, 0, 0, 0, 1, 0, and 0, 0, 3. We could, of course, also have done the multiplication step for that last vector. I just didn't want to bother with that. But that would also yield a perfectly good solution. Now what we have obtained here is this one vector here. That vanishes now. Plus, what you can see very obviously, almost very obviously, is here's only one entry here. One entry here, and in row 1, this vector has the only entry. So if we want to obtain the 0 vector as a linear combination of those 3 here, the only chance to get the first coordinate to 0 would be to take 0 times the first vector. And then for the remaining 2, the only chance to get coordinates 2 and 3 to 0 would be to take 0 times the third vector and 0 times the fourth one. So we can see this is a set of linearly independent vectors. So 2, 1, 3, 0, 1, 0, and 0, 0, 3. That set here, this is linearly independent. And therefore, we have a basis. We didn't change the span with our operations because we only took linear combinations within that set and recombined the vectors that we have. the span is still M. So this here is a basis of M. And therefore the dimension of M is the cardinality of the basis. The dimension of M is 3. And we also found out that the second vector in our set is actually a linear combination of the remaining 3. So also V2 is a linear combination of V1, V3, and V4. So with that knowledge, we could also say we're taking V1, V3, and V4 as our basis, because we know that generates M. V2 can be eliminated because it's just a linear combination of those 3. And by now we also know the dimension of M is 3, so we need 3 vectors in our basis. We cannot eliminate another vector here. So if we do this, let's have a look back here. Then V1, V2, V1, V3, V4, that would be this set of vectors here. So that would also be a valid solution. Okay, so that's set 2, 1, 3, that's V1. 2, 3, 3, that's V3. And -2, 3, 0 is also a basis of M. And this is one that consists of vectors that were originally given. So one might prefer that the basis that we got here has vectors that are different from the ones that were given originally. On the other hand, it looks simpler. So depending on the application you have in mind, one of these might be preferable to the other. Now, if you look back at the procedure we did here, basically we took one vector, this one here, to eliminate the first row for the others. Then we took another vector, this one here, to eliminate the second row for the others. That should look familiar. And actually what we did here is basically Gaussian elimination. So this procedure is almost Gaussian elimination. But in particular, we could write it as a Gaussian elimination. If we just write the vectors as rows of a tableau, then manipulate those rows using Gaussian elimination operations, elementary operations, we would obtain a valid result. Maybe the same as we have here, maybe a different one, but still a valid basis. In particular, if we take care to not permute any rows in that process, or take note of the permutations that we actually do, we will also be able to tell which of the original vectors would form a linearly independent set. So here's what we could also do. We could also write the vectors as rows of a tableau we could then perform Gaussian elimination on those. Only thing we'd have to take care of is we either have to take note or prevent permutations of rows. So take note of row permutations or avoid them altogether. And that's important if we wanted to see the bases in terms of the original vectors. So let's try. What does that mean here in our example? So the vectors we have, again, I'll write those down. 2, 1, 3, 4, 1, -1, 2, 3, 3, and -2, 3, 0. Remember? Now we could write those as rows of a tableau. So we write 2, 1, 3, 4, 1, -1, 2, 3, 3, and -2, 3, 0. And then basically, doing an elementary operation amounts to replacing one of the rows, so one of the vectors, by a linear combination of that row and some other row. And that's just the same thing that we did with the vectors. So let's do Gaussian elimination here. This is our first pivot element. We'll subtract the first row twice from the second. We'll subtract it from the third. We'll add it to the last one. And that way we obtain, let's see, 2, 1, 3. Second row becomes 0, -1, -7. That looks familiar. Third row becomes 0, 2, 0. That also looks familiar. And finally we get 0, 4, 3. And you notice we obtained these vectors already. Now in our computations before, we continued with this vector here. In Gaussian elimination, we would usually use the second row. And remember, we don't want to permute the rows if we can avoid it. So let's continue with this one in a traditional Gaussian elimination way. The result will probably be different then, but still we will get a basis of M, and of course the dimension. Okay, so what we're doing is we add this second row twice to the third one, and we add it 4 times to the last one. That yields, let's see, 2, 1, 3, 0, -1, -7, 0, 0, and -14, and 0, 0, and -28. Oh, sorry, not -28. My bad. I forgot about the 3 here, so it's -25, of course. Well, and finally, let's subtract 25 over 14 of the third row from the fourth. And that will result in a tableau in echelon form, like this here, 1, 0 row. We get 3 pivots. That means the dimension of M is 3. And we get a basis for M. And that is the remaining non-zero rows, the pivot rows. We just take those and write them as vectors again. So we have this 2, 1, 3, 0, -1, -7, and 0, 0, -14. And you notice the result is different, but it's still a basis of M, and there are lots of bases for M. So this is a completely valid solution. And again, the reason why I'm doing this using Gaussian elimination is not because there is really a system of linear equations involved here. It's just because the steps that I'm using for taking these successive linear combinations, those steps are basically elementary operations. And that means I can handle that the same way I handle Gaussian elimination. And because I practice Gaussian elimination a lot, and I'm using it on a very regular basis, I know how to do that. So why not use a method that I know by heart to solve a problem that is seemingly harder? That's the only reason why I'm using this process. Finally, one last comment here. Dimension of M is 3. M is a subset of R to the 3, so that means, of course, M is R to the 3. Okay, just to mention that as well. So M is the whole space it's contained in. So that concludes our little examples about bases and dimension and linear independence. We'll revisit those notions a lot more in the coming videos when we apply them in different contexts. But for now, let's conclude with these examples here. We'll have a look at an application, an economic application, in one of the upcoming videos. And we're going to close that section with a look at affine spaces, also in one of the next videos, to conclude our investigation into the solution spaces of systems of linear equations. I'll see you then.